All right, let's check out some sample problems. They're going to look very much like the other problems that we have looked at, so these are all going to kind of be the same. I'm going to let you know right now that all these are at the equivalence point, and they are all a strong, weak situation. So number one here is a pretty obvious one. You've got 50 milliliters of 0.2 of this guy here who's ugly looking but weak. And then you're going to mix that with 50 milliliters of 0.2 of this strong one over here. So we are most definitely at the equivalence point. So we are going to start here with our weak acid. It's going to be 50 100ths of 0.2 molarity of, I think this is benzoic acid, HC6H5CO2, which again is going to then be a 0.1 molarity after it's all said and done. And then you got a strong base situation that's going to be 50 100ths of 0.2 molarity of the OH negative, because again, we're just going to get rid of the potassium because it's a spectator ion. So that's going to be 0.1 molarity as well. So as presented to you, the problem is HC6H5CO2 plus OH negative is going to come over here and form H2O plus the conjugate base, which is C6H5CO2 negative. You need to recognize that this is not the format that you want to be using. These are not the droids you're looking for, because the water is on the products side over here. So instead of starting with 0.1, 0.1, and 0 and trying to do a left to right problem, we are instead going to take it all the way to be left with 0, 0, and 0.1 over here, and then take this whole thing and flip it and do a backwards problem. So what we're going to then do is we're going to do a KB problem. C6H5CO2 negative plus a water is going to come over here and form hydroxide and the conjugate acid. And the reason that we're going to do that is because it is Ka. Now again, they did not give us Ka. I'm sorry. It's Kb. Sorry, I got my alphabet soup backwards. I apologize. This is Kb because this is the backwards of the situation. We have OH negative, that's Kb. My bad. So they did not give us Kb, they gave us Ka. But in giving us Ka, they give us Kb. So Ka times Kb is equal to 1 times 10 to the negative 14th. So we're just going to divide that out. 1 times 10 to the negative 14th divided by 6.3 times 10 to the negative 5th is going to get a Kb situation of 159 times 10 to the negative 10th. So remember that that number times that number always equals that number. So if you have one, you have both. If you have the acid, you have the conjugate base. If you have the base, you have the conjugate acid. You know both, even though they might not have given you both. So what was it? 159 times 10 to the negative 10th. So this is 159 times 10 to the negative 10th. So now I do an I, a C, and an E, and now water is on the left-hand side, which is where we want it. It's a 0.100. This looks familiar. This goes back to part 1 that Mr. Comerford talked to you about. This is going to be a minus x plus x situation, and it's going to be a 0.1 minus x, x, and x. And again, you can get rid of this guy here if you want to. I know I always like to, because it'll make your math life considerably easier. X squared over 0.1 is 159 times 10 to the negative 10th. And so x is equal to times 0.1, and then square root that guy. You're going to end up with 3.99 times 10 to the negative 1, 2, 3, 4, 5, 6, it looks like. 399 times 10 to the negative 6th, and that x is the same thing as OH negative. So if I were to take the negative log of that number, I would get a POH then of 5.4, which makes then a pH of 8.6? Yeah, 8.6. pH of 8.6, which again makes sense that it's slightly basic because we are doing a weak acid with a strong base that's here, and we are doing it to the equivalence point. So the strong base is going to win in equal amounts with the weak acid that's there, which is why we end up with a slightly basic pH down